Welcome to lecture series on digital electronics under EPG Pathshala. There are two types of digital circuit. The first one is a combinational circuit and the second one is sequential circuit. So far we have discussed simple combinational and sequential circuits. In this module, we will be learning about sequential circuit basics and the finite state model. Now, whenever we talk about designing or analysis of any sequential circuit, it is necessary to consider certain tables other than only truth table. So, whenever we talk about the generalized model for sequential circuit, it consists of combinational circuit and the memory. There is a feedback such a way that we can remember the previous state. So, whenever we talk about sequential circuit, there are certain number of sequential states the counter can undergo. There could be a shift register which can shift maybe through several states. So, whenever we talk about sequential circuit, we come across several different states and these states are usually finite in number. That is why we always prefer to have a finite state model or finite state machine. Whenever certain finite state machine is to be considered, we need to talk about simple block diagram, and this block diagram consists of some memory combinational blocks, and these combinational blocks could be used at the input side as well as output side, and these three things together can give you 5 different types of sequential circuits. There are 5 types of finite state models. The first one is a class A, class B, class C, class D and class E. So, whenever we talk about these models, the combination is dependent upon whether you have feedback or feed forward mechanism implemented in the system, or whether input or output combinational blocks are present or absent. So, we can have a variety of sequential circuits. In addition to that, whenever we design the circuit, we need to talk about several other parameters of the memory or a flip flop. The flip flop behavior can be described well in terms of characteristics table. From that we can derive the characteristics equation. In addition to characteristic equation, we need to define the behavior of the system with the help of either state diagram or state table. So, whenever state diagrams or state tables are ready, we can definitely move towards the next part, that is knowing the excitation table or transition table. So, these are the several terminologies that we have to use whenever we talk about sequential circuit design or analysis. Now, in this module, we will focus it on learning these different terminologies in sequential circuit as well as finite state model. Slide 4. Let us discuss the learning objectives of the module. The first objective is to understand the concept of finite state model. There are different types of sequential circuits. The models are normally used to describe different sequential circuits which are categorized as class A, class B, class C, class D and class E. To use finite state machine, it is important to create characteristics table, characteristics equations and excitation tables of different flip flops. Further, it is important to learn the method of preparing state diagrams and state tables. The sequential circuit can be represented by a basic modeling structure, so as to understand how flip flops play important role in sequential circuits. Models provide a means to represent an idea, concept or a process mathematically or graphically. This helps in enhancing the understanding of sequential circuit. The universal model for sequential circuits shows how combinational circuits and memory or flip flops are correlated to each other. The universal model includes all the elements of sequential circuit. Combinational circuits accepts binary input variables x 0 to x n and generates output variables y 0 to y n. In addition, the system generates excitation variables E 0 to E k and accepts state variables S 0 and S k as past inputs which are stored in the memory. Thus, the output of sequential circuit is the function of present input conditions x I and past inputs provided by the state variables S I. The memory elements will always appear in the feedback path. To study a sequential circuit, it is important to know the internal state of the circuit. The flip flops are normally used in the feedback path with combinational circuits to form a sequential circuit. This circuit follows a sequence of internal states. Each internal state is characterized by set of allowable states. The input conditions determine which of these allowable successive states the system can undergo. The sequential circuits are classified into two categories: synchronous sequential and asynchronous sequential circuit. An asynchronous sequential circuit, the contents of memory, that is flip flops, can be changed only at rising or falling edge of the clock signal. In asynchronous sequential circuit, the contents of memory can be changed at any instant of time. Let us now talk about different terminologies used in the state machine. These are called as state machine notations. There are 5 different types of terminologies: input variables, output variables, state variables, excitation variables and the state. Input variable is the one wherein all the variables which are external to the sequence circuit are defined. There are finite number of input variables represented by the symbol x. Say for example, x is equal to x 0, x 1, x 2 up to x n. Now, let us talk about output variable. All the variables that exit the sequential circuit are referred to as output variables. There are finite number of output variables represented by the symbol y, as y is equal to y 0, y 1, y 2 up to y n. Let us now talk about state variable. The output of memory defines the state of sequential machine. The output of flip flop defines the state variables. There are finite number of state variables represented as s is equal to s 0, s 1 up to s k. Let us now discuss excitation variable. Excitation variables are defined as the inputs to the memory, that is flip flops. The name excitation is used because the variable excites the memory to change its state. So, when the flip flops are used as memory, the excitation variables are the inputs to the flip flops, that is j k, s r, d or t inputs. State variables are the function of excitation variables. Excitation variable E are the function of input variables and the state variables S. The state of sequential circuit is defined by the contents of memory. The state is defined by output Q. Each state of sequential circuit should be unique and unambiguous. So, for k flip flops there will be 2 raised to k number of possible states. Let us now talk about present state and the next state. State machines normally use synchronous sequential circuit. Usually rising or falling edge triggered flip flops are used. Flip flops can change state only on clock pulse edge, hence it is necessary to distinguish the state variable before and after the clock pulse. State variable x can be represented by x t before the arrival of the clock pulse and x t plus 1 after the arrival of the clock pulse, which is shown in the diagram. The status of state variable at any instant of time t before the application of next clock edge is called as present state. The present state is taken as a reference point with respect to time. The status of all state variables at some time t plus 1 after the application of clock edge is called as next state. The next state is represented by flip flops status after a particular clock time t. Present state and next states are normally used to prepare the state table of the state machine. To study sequential circuit, it is necessary to know the internal state or condition of the circuit. Flip flops, counters, shift registers are sequential logic circuits. All these circuits follow a sequence of internal states. The sequence of internal states is produced by a sequence of inputs. Each of the input state is characterized by a set of allowable successful states. The input condition determine which of these allowable successful states are generated next. Let us now discuss the state diagram and state table for a sequential circuit. A state diagram is a graphical representation of the sequential circuit. Individual states are represented by a circle with an identifying symbol located inside. Let us consider a simple circuit having two states 0 and 1. This circuit has an external input x and the state of the circuit are shown by encircled numbers 0 and 1. Changes from one state to another are indicated by an arc with an arrowhead at one end. Input condition that causes state changes are written adjacent to the directed arc. It is possible to represent state and self transitions in the state diagram. When the circuit is in the state 0 and if input x is equal to 0, then the state remains in the state 0. This is known as self transition. If the input x becomes 1, then the circuit makes transition from state 0 to state 1. This is referred to as state transition. When the circuit is in state 1, if x becomes 1, then the circuit remains in the same state, then self transition takes place. When x changes to 0, then the circuit switches to state 0. This results in state transition for the circuit. The behavior of the sequential circuit can also be represented by a state table. State tables are tabular forms of the state diagram. The first column in the state table represents all possible present states and there are a series of next state columns, one for each input combination. The purpose of state table is to indicate the state transition. A two state one input variable state diagram is converted into state table as shown here. First column indicates two possible present states 0 and 1. The circuit will change the state depending upon the value of input variable x. When the present state of the circuit is 0 and x is also 0, then the next state of the circuit remains in 0. But if x is equal to 1, then the next state of the circuit remains in state 0. Similarly, when present state is 1 and input variable x is also 1, then the next state of the circuit remains in state 1. But if x is equal to 0, then the next state is 0. State table gives the complete information about present states, next states, inputs and outputs of the sequential circuit. A sequential circuit has number of output states corresponding to different input and output combinations. Say for example, a decade counter produces 10 different states. Such a circuit is called as finite state machine. Let us consider a structure of finite state machine as shown in this diagram. This is basically a generalized sequential circuit model. It has input output combination logic, popularly known as next state decoder. It decodes the input x and the present state P s of the machine and generates the next state. The next state is a function of both input and the present state. The next state information becomes the present state at memory which it stores it. As a generation of next state and present state is a continuous process, present state information is fed back to generate the next state with the help of present inputs. These present input conditions are also forwarded to the output decoder through a feed forward path. These inputs with present state generates the necessary control signal at the output of the state machine. The output of finite state machine is given by y is equal to G function of x and Ps. Finite state machines are classified according to the feedback, feed forward as well as other connections as class A, that is milli state machine, class B Moore state machine, class C, class D and class E machines. In the model of finite state machine, the next state is also referred to as excitation variable for exciting or triggering the flip flops present in the memory. Similarly, the present state generates the state variables for the next state decoder. The class A state machine is popularly known as Milli machine, named after the logic designer Milli. It consists of three major blocks: next state decoder, memory and output decoder, along with feedback and feed forward mechanisms. The basic property of Milli machine is that output is the function of present input conditions and the present state. Let us now talk about Moore machine. The class B state machine is known as Moore circuit, named after the logic designer Moore. The basic property of Moore circuit is that its output is strictly a function of present state of the sequential circuit. Careful observation of Moore machine shows that feed forward mechanism is absent in the state machine. Therefore, the output is a function of only present state. Both Milli and Moore machines are widely used. In some cases, it is not possible to get the circuit that are combination of both. That is, some outputs are depend on both inputs and present state of the state machine. Other outputs depends on present state of the state machine. In the class C state machine, the output decoder is not required to generate the output. The output of state machine is nothing but the present state of the state machine. The generalized model for counter represents basically the class C state machine. In such circuit, the events to be counted are entered through the next state decoder. In class D machine, the outputs are directly obtained from the output of memory, that is the present state of the state machine. The comparison of class D with class C state machines indicates that there is no feedback of present state to decide the next state. The next state is decided directly by the input combination. Example of such circuit is a presettable counter, where starting value of a counter is decided by the external input. Another example of class D machine is the lookup memory. The class E state machine is the simplest sequential circuit model consisting of only the flip flops as the memory element without any combinational circuit. Ripple counter can be considered as the example of class E state machine. Role of flip flops as memory is very important in the finite state machine. Before designing the state machine, it is important to look at the behavior of the flip flop. The behavior of the flip flop can be uniquely described by its logic symbol, characteristics table, characteristics equation, excitation table, state diagram and state table. Let us begin with the SR flip flop. The characteristics table defines the state of each flip flop as a function of its SR inputs and previous state. With reference to clock pulse, Q represents the present state and Qt plus 1 represents the next state after the clock pulse. The characteristics table for RS flip flop is represented by writing present state, SR as inputs in the initial columns and the next state in the last column. First 4 rows assumes that Q is equal to 0 and Q is equal to 1 for the next 4 rows. All possible input conditions for S and R inputs are written for a group of 4 rows. The characteristics table for SR flip flop shows that the next state is equal to the present state when both S and R inputs are equal to 0. When R is equal to 1, application of clock pulse resets the flip flop. When S is equal to 1, the flip flops are set to 1. When both S and R inputs are 1, the output state is unknown, undeterministic. For such case, let us consider the output as question mark or X, that is don't care condition. To obtain the characteristic equation for the flip flop, it is necessary to use K maps for simplification of Boolean expression. For SR flip flop, K maps for 3 variable is required with Q and SR as inputs. Let us map the next state Qt plus 1 in the K map. First two next state conditions are zeros. In the third row, Q is equal to 0 and SR is equal to 1 0. The next state 1 is mapped into the K map. Fourth row with Q is equal to 0 and SR is equal to 1 1, the next state X is mapped. The fifth row with Q is equal to 1 and SR is equal to 0 0, the next state 1 is also mapped. Seventh row with Q is equal to 1 and SR is equal to 1 0, the 1 for next state is placed. Last row with Q is equal to 1 and SR is equal to 1 1, the X is mapped into the K map. Let us group the chord as marked in yellow for visual simplification. First and last row helps us to form a pair. The chord eliminates 2 variables and provides the term S. The pair eliminates the S and provides the term R bar Q. Thus, the characteristics equation for SR flip flop is given as Qt plus 1 is equal to S plus R bar Q. Let us now talk about characteristics table and equation for D flip flop. The characteristics table for D flip flop is prepared by writing present state, D inputs in the initial columns and next state in the last column. In the characteristics table, the next state of the D flip flop is completely dependent on the input D and independent of present state. Let us map the characteristics table in 2 variable K map. The next state is mapped as 1 when Q is equal to 0 and D is equal to 1. Further, the next state is mapped as 1 when Q is equal to 1 and D is equal to 1. Let us form the pair to eliminate one variable. The characteristics equation for D flip flop is Qt plus 1 is equal to D. The JK flip flop is most popularly used in many sequential circuits. The characteristics table for JK flip flop is prepared by writing present state, JK inputs in the initial columns and next state in the last column. The characteristics table for JK flip flop is similar to SR flip flop except the unknown condition. When both J and K are equal to 1, the next state is equal to the complement of the present state, that is Qt plus 1 is equal to Q bar. Let us prepare a K map of 3 variables Q, J and K. The next state 1 is mapped when Q is equal to 0 and Jk is equal to 1 0. Similarly, when Q is equal to 0 and Jk is equal to 1 1, then the next state 1 is mapped. When Q is equal to 1 and Jk is equal to 0 0, the Qt plus 1 is equal to 1 is mapped. The next state 1 is mapped when Q is equal to 1 and Jk is equal to 1 0. Let us form the groups. It is possible to have pair for next state as shown here. First and last columns are neighbors of each other, hence we can form this pair. First group results in Jq bar, the second group results in K bar Q. Thus, the characteristics equation for Jk flip flop is Qt plus 1 is equal to Jq bar plus K bar Q. Let us now prepare the characteristics table and equations for T flip flop. The characteristics table for T flip flop is prepared by writing present state and T inputs in the internal columns and the next state in the last column. In the characteristics table, the next state of T flip flop is the same as the present state if T is equal to 0 and the next state is complement when T is equal to 1. Let us map characteristics table in two variable K map. With Q is equal to 0 and T is equal to 1, the next state 1 is mapped. Further, when Q is equal to 1 and T is equal to 0, the next state 1 is mapped. It is not possible to simplify the K map. Therefore, the characteristics equation of T flip flop is given by Q T plus 1 is equal to T Q bar plus T bar Q. The characteristics table is useful during the analysis of the sequential circuit when the values of the flip flop inputs are known. It is necessary to find out the value of next state of the flip flop. The K maps are used to derive the characteristics equation from the characteristics table. During the design process, one of the important tasks is to find out the flip flop input conditions when the present state and the next states are known. For this reason, excitation table is introduced to know the flip flop excitation inputs from the given states. Let us now prepare the excitation table for SR flip flop. In order to obtain the excitation table of the flip flop, it is necessary to list all possible present state and the next states and obtain the input conditions to generate such state change. If both present and next states are equal to 0, then SR inputs should be 0 x. Here x means do not care condition, that is the input can be either 0 or 1. If present state is 0 and next state 1 is desired, then SR inputs should be 1 0. Transition of present state 1 to next state 0 can be obtained by setting SR inputs to 0 1. The SR input should be x 0 for 1 to 1 transition of the present to next states. To obtain the excitation table of JK flip flops, it is necessary to list all possible present state and next states to determine the input conditions to generate such state change. If both present and next states are equal to 0, then JK input should be 0 x. Here x stands for do not care condition, that is the input can be either 0 or 1. If present state is 0 and next state is 1, then JK input should be 1 x. Transition of present state 1 to next state 0 can be obtained by setting JK inputs to x 1. The JK input should be x 0 for 1 to 1 transition of present to next states. The JK flip flops are normally preferred for almost all designs because the excitation table indicates do not care input either at J or K inputs for all present to next state transitions. This helps in eliminating many terms from the next state equations. To obtain the excitation table of D flip flop, it is necessary to list all possible present state and the next states to determine the input conditions to generate such state change. If both present and the next states are equal to 0, then D input should be 0. If present state is 0 and next state 1 is desired, then D input should be 1. Transition of present state 1 to next state 0 can be obtained by setting D input to 0. The D input should be 1 for 1 to 1 transition of present to next states. To obtain the excitation table of T flip flop, it is necessary to list all possible present state and next states to determine the input conditions to generate such state change. If both present and next states are equal to 0, then T input should be 0. If present state is 0 and next state is 1, then the T input should be 1. Transition of present state 1 to next state 0 can be obtained by setting t input to 1. T input should be 0 for 1 to 1 transition of present to next state. In the sequential circuit, the output of the circuit at any instant of time depends upon its present state and the inputs. These also determine the next state of the circuit. The relationship between inputs, outputs, present state and next state can be specified by either state table or state diagram. Let us now prepare state diagram for SR flip flop. A state is represented by a circle. There are two states for all flip flops. Flip flop can be reset state when q is equal to 0 and in the set state when q is equal to 1. From the excitation table, it is clear that all the flip flops can have 4 possible transitions. The transitions between the states is indicated by directed lines or arcs connecting the circle. Two of them are referred to as self transition and rest 2 are state transitions. If SR flip flop is in reset state, that is q is equal to 0 and SR inputs are 0x, then the flip flop remains in the same state. Here x value can be either 0 or 1, that is do not care condition. But if SR inputs are 1 0, then flip flop makes 0 to 1 state transition. Similarly, when flip flop is in set state, that is q is equal to 1 and SR inputs are x 0, then flip flop remains in the same state. But if SR inputs are at 0 1, then flip flop makes a 1 to 0 state transitions. Let us now prepare the state diagram for JK flip flop. Even JK flip flop has two states, reset and set state. Let us prepare the state diagram with the help of excitation table. If JK flip flop in the reset state, that is q is equal to 0 and JK inputs are 0x, then flip flop remains in the same state. But if JK inputs are 1x, then flip flop makes 0 to 1 state transition. Similarly, when flip flop is in set state and JK inputs are x 0, then flip flop remains in the same state. But if JK inputs are x 1, then flip flop makes 1 to 0 state transition. Let us now prepare state diagram for D flip flop. There are two states, reset state and set state. If D flip flop is in the reset state, that is q is equal to 0 and D input is 0, flip flop remains in the same state. But if D is equal to 1, then flip flop makes 0 to 1 state transition. When flip flop is in set state, that is q is equal to 1, the D input is 1, then flip flop remains in the same state. But if D input is 0, then flip flop makes 1 to 0 state transitions. Let us now prepare the state diagram for T flip flop. There are two states, reset and set states. If T flip flop is in reset state, that is q is equal to 0 and T input is 0, then flip flop remains in the same state. But if T input is 1, flip flop makes 0 to 1 state transition. When flip flop is in set state, that is q is equal to 1 and T input is 0, then flip flop remains in the same state, that is self transition. But if T is equal to 1, then flip flop makes 1 to 0 state transition. Let us now sum up the things that we have studied in this module. We have discussed finite state machine. In this finite state machine, there are finite number of states the sequential circuit can undergo. There are 5 number of different types of state machines. These finite state machines are classified as class A, class B, class C, class D and class E. This is dependent upon how many flip flops those are used, whether the input and output decoders are present or absent, and there are several other combinational circuits. In addition to that, we have seen there are 5 basic parameters we need to consider while designing or analyzing the sequential circuit. These are characteristics table, characteristics equation, state table or state diagram and excitation table. So, these are the different kinds of parameters or terminologies that we have defined while analyzing or designing any complex sequential circuit. Thank you.